If you're familiar with the wave equation, you will know that a function of the form psi of x and t, so it's a multivariable function which depends on x, which can be the horizontal displacement, and time t, is equal to a tilde, and I'll explain what the tilde means, times e to the I kx, where k is the wave number, minus omega t, where omega is the angular frequency. Now, obviously, a trigonometric function of the form a times cosine kx minus omega t plus phi can also be a solution to the wave equation, but we will use the complex representation because we will see it has some mathematical advantages. Now, the factor a tilde is actually a complex number. And the reason for that is because this factor over here encodes the phase offset. And what I mean by that is that a tilde is actually equal to a times e to the I phi. So essentially, a is the maximum amplitude of our function psi of x and t. But we also put the phase offset into the amplitude. So for example, we could have written the equation as a e to the I kx minus omega t plus phi, which is how we traditionally write a sinusoidal expression. But in this case, we're going to put the phi over here in the a tilde. Now, let's call this function psi1. And we have x1 over here. And psi1 is one solution to the wave equation. Now, let's say we have another solution to the wave equation, psi2, which depends on x2, is equal to a tilde 2 e to the I kx minus omega t, well, kx2 minus omega t. If these two functions are solutions to the wave equation, then the sum of these two solutions is also a solution to the wave equation. And physically, what this means is that when we add two waves, so the first wave is represented by psi1 and the second wave is represented by psi2, when we add these two waves, we essentially get another wave, and therefore the sum also satisfies the wave equation. And so amplitudes add up. From a mathematical standpoint, this is due to the linearity of the wave equation. In nature, however, detectors measure the energy or the intensity of a wave and not the amplitude in itself. In particular, detectors measure the intensity, the average intensity, over many cycles. And the reason we do an average is because waves generally have high angular frequency, and therefore detectors don't have enough precision to measure that frequency. And so what detectors do is they do an average over many cycles. And the intensity averaged over many cycles can be expressed mathematically. I might show this in a future video, but generally intensities can be written in the form alpha, where alpha is just a constant, times the modulus squared of psi, the mathematical expression of the wave. So what we're interested in is not how the amplitudes superpose, but rather how intensities add up. And notice here that the modulus squared is not a linear operator. Remember that when two waves meet, well, the total amplitude is just the sum of the amplitude of each function. And this is due to the linear property of the wave equation. However, the modulus squared is not a linear operator, unlike the wave equation. So we will see that intensities act quite differently. In particular, we will show that the total intensity of the sum of two waves is not equal to the sum of each individual intensity. So in the next video, I'll derive the formula for how to add intensities. So let's do a recap of everything that we just saw. Waves can be expressed mathematically in this form where we have a complex exponential. And one key property about waves, and so functions that satisfy the wave equation, is that when we have two solutions to the wave equation, and therefore two waves, if we add them up, we also get a wave. And therefore, the sum of two solutions is also a solution to the wave equation. And this is due to the fact that the wave equation involves differentiation, and differentiation is a linear operator. Furthermore, the linearity property is translated physically by this idea that we can superpose waves, that we can add them up. However, detectors measure the intensity, which is the energy per unit area of the wave that goes through the detector. And the intensity is expressed by this formula. And we can note that we're taking the modulus squared of the amplitude function. And because of this, we don't preserve this linearity property. In other words, the total intensity of the sum of two waves is not the sum of the intensities of each wave.